This is my presentation for Lab 1 for physics on constant velocity. This lab measures position versus time that's constant, or constant velocity, and it uses the principles of the momentum principle, or second law of motion, and the first law of motion. I showed these two principles and constant velocity experimentally, and then I compared the data that I got from that to a computer model that was meant to predict the motion. For my results, I found a close match between the two, but not exactly the same. The first model that I used was the momentum principle, or the second law of motion. These two names describe the same exact equation, just rearranged to get different variables, but meaning the same exact thing. The second law of motion is obviously force equals mass times acceleration, which is rearranged then to become net force equals a difference in momentum over a difference in time. Because mass doesn't change in the experiment, a difference in momentum must mean a difference in velocity, and if there's no net force, that means there's no acceleration, and therefore no difference in velocity and no difference in momentum. This is used to explain how having no net force would mean that an object experiences constant velocity and not accelerate. And I had made the assumption for my experiment that there is no net force on my moving object. I also used the first law of motion to explain how the rolling object would remain rolling in the same speed and direction because it was not acted upon by an outside net force. And that explains its path. For my experiment, I hand-rolled a tennis ball across a carpeted floor at about standard temperature and pressure, and the speed that the ball was released at was about walking speed. I filmed the ball from a side angle on the floor, and the ball rolled from left to right on the screen. The position of the ball was identified with tracker software that used 1/30th second increments to map out the position over time. And the position values are unscaled, meaning that they're not accurate to real-life values, but they are relatively correct. For the coding, I used GlowScript or Python software originating from a starter code to model the experiment, and I also made the assumption that there's no net force on the object and therefore a constant velocity. The initial velocity, or the permanent velocity for the code that I used, was the average velocity that I measured on the tracker data from 0 to 0.1 seconds, and then from there I measured every 1/30th of a second over 0.6 seconds, just like with the tracker data, to produce a set of values. The initial position was 13.78 meters, which is the same as it is on tracker at 0 seconds. As you can see in the graph, the experiment and the model follow a pretty close path, but towards the end, the experiment starts to fall away from the model, which would indicate that it was not perfectly modeled. This discrepancy between the two can be put down to deceleration or a change in velocity, because the slope towards the end is not as steep as it is in the beginning for the experiment. However, both the experiment and the model seem to follow about the same path from 0 to 0.3 seconds. So for smaller time increments, for smaller values of time, the model seemed to work pretty well. The position is about linearly proportional for both, although it's exactly linearly proportional for the model and not exactly so for the experiment. Because of this difference in velocity from the beginning to the end, that means that there has to have been some net force in the experiment, according to the first and second laws of motion, and also a change in momentum over time. The model doesn't experience any net force, and because of that, it has constant velocity and momentum and a linear path of position over time. Sources of error could be inaccurate identification of position with tracker, which would be random error, and inaccurate and imprecise calculations of the initial velocity used in the code, and that would be a systemic error. For my conclusion, I said that the coded model wasn't a perfect prediction of the object's motion in the experiment because it overestimated the velocity toward the end of the period of filming, and it did not take into account a net force that the tennis ball experienced according to the first and second laws of motion. The net force was in a direction opposite to that of velocity, and that's seen in how it slows down, which would only happen if that was the case. And this net force is likely friction between the ball and the floor. Further questions: if the x-axis was flipped This would not fundamentally change the conclusions from this experiment, but the graph would look different because instead of going in the positive x direction, the position of the ball would be going in the negative x direction. But so as well would the ball model be going, so it wouldn't change much. It is also possible to say that there are two forces acting in the y-axis, force of gravity and force of normal force.